Our pigeonhole principle, a very basic idea. If we have n plus 1 or more objects and we have to place them in n containers, holes, call them whatever you like, then at least one of those holes must contain 2 or maybe more objects. Okay? That's the idea. Alright, so let k be the maximum number of objects you can put in those n holes without having more than one object in a hole. We're going to prove that k is indeed less than n plus 1. I've called it a proof. Is it a proof? Well, let's see. I'm going to assume the opposite. I'm going to assume k is actually greater than or equal to n plus 1. The number of objects I have is greater than or equal to n plus 1. The maximum number of objects must be n. In other words, each hole would have one object. Remember we said we don't want to have more than one object in a hole. So therefore k has to be less than or equal to n. Yet we assumed k was greater than or equal to n plus 1. Well, that's a contradiction. So it's that proof by contradiction idea. Thus, my assumption must have been wrong. It can't be true that k is greater than or equal to n plus 1, so k must be less than n plus 1. As I say, is it a proof? Yeah, well, it sort of is. In general, here's how we can do it. If you've got k or more objects and you want to place them into n holes, then at least one hole must contain k over n. Now you might not know what that notation is, but I'll explain in a sec. Or more objects. That notation is what's called the ceiling function. The ceiling function is like a set of brackets, but with the bottom chopped off. There is also something called a floor function, which has the top cut off and it has the bottom part of the brackets. But what it's basically saying is, well, x must end up being in between y minus 1 and y. It could include y, but it doesn't include y minus 1. Or another way of thinking about it is, whatever the answer is, you always round up regardless. Even if it's 0.2, round up. That's basically what a ceiling function does. It gets it and raises it to the ceiling. We are going to select integers from this set of numbers, consecutive numbers going from 3 to 12. We want to know what's the least number of integers needed to ensure that we do get a pair of numbers that adds up to 15. Well, when we look at these numbers, there actually are 5 possible pairs that will end up adding to 15. And there they are. So these new sets that I've done, if you like, are like the pigeonholes. 3 goes with 12, 4 goes with 11, 5 goes with 10, 6 goes with 9, 7 goes with 8. So the number of holes, containers, whatever you want to call them, is 5. Therefore, by the pigeonhole principle, we need to select 6. One more the number of holes, and that will guarantee that we have a pair. Because if I only had 5, I might not have a pair. I might choose 3, and then in the next one I might have 11, I might have 5, 6 and 7. There's 5 numbers I've picked. None of them add up to 15 when we group them together. But as soon as I get one more number, I must have a match with one of those. So one more, 6. And that's basically it. That's your pigeonhole principle. If I did it using our ceiling function, I could have done it like this. So k, how many objects, that's what I'm trying to find, over n, the number of containers, holes, 5, but I know the answer to this is 2. So that's what I'm solving. Well, that tells me then that k over 5 must be in between 1 and 2. It could include 2, but not 1, which means k must go in between 5 and 10. Well, I can't have 5. I want the smallest number, so 6 would be the smallest number that would satisfy that. So there are 6 integers I could select. So that's how I could do it algebraically. The first way, I guess I'm doing it just logically, thinking about it. 50 points, we're going to place them in a 7 by 7 square. What's the maximum distance apart that the 2 closest points could be? So all those points, we put them in, and we're saying, what are the 2 closest points? What's the furthest away I could place them? Well, that square, 7 by 7, I could divide it up into 49 1 by 1 squares. Each one of those squares could become a container, if you like, where the dots are going to be placed. Okay? So they're my holes. So the pigeonhole principle tells us if there are 50 points, there must be a square that contains at least 2 points. Now, why is that important? Well, because if I had less than 50 points, then it might be there's one in every square. Remember, I want the two that are closest together. So if I've got 2, if I can guarantee I've got 2 in one hole, then those 2 points have got to be the 2 closest points. Now the question becomes is, what's the maximum distance between those 2 points if they're in the same hole? We're talking about a square. It'd have to be at either end of the diagonal in that square. Well, a bit of Pythagoras, square root of 2. So that would be the maximum distance that a closest pair of points could be, would be the square root of 2 units. We're going to prove that in a group of n people, there will always be at least 2 people with the same number of friends in that group. Right, so some might have 1 friend, some might have 2 friends, some might have 3. But there will be at least 2 people that have the same number of friends. Now let's think about this. It would be impossible for one person to have no friends and another person to have n-1 friends. That would be impossible. Because let's just say, here's everyone. Sorry about this, but you got no friends. Okay? No friends. Okay? But what we're saying is that there'll be someone else who's very friendly. Right? That everyone in the room is your friend. Well, that's impossible because you've got no friends. So you can't have both. We could have one of those situations, but both. So what I'm getting at is the possible number of friends a person could have. I've decided that the no friends is the one that's not going to happen, because that's nicer. So we could have 1, 2, 3 up to n-1. I mean, I could have gone 0, 1, 2, 3 up to n-2, I suppose, but it's still the same number of possibilities, same number of holes. There's going to be n-1 different number of friends that we could have. There's our containers, our hole. Well, by the pigeonhole principle then, there must be at least 2 people with the same number of friends, because remember, we've got n people. There's n people, n-1 holes, then someone must go in 2 containers. Sorry, there must be 2 people that go in the same container, in the same pigeonhole. 16 positive integers are written on the board. At least how many numbers will have the same remainder when we divide those numbers by 5? There are 5 possible remainders. 0, 1, 2, 3 or 4. We are going to place those 16 integers on the board into one of those containers to see what their remainders are. I'm going to use the ceiling function for this. So 16 objects into 5 holes, so 16 over 5. That's 3.2, but we always round up. So there must be at least 4 numbers on that board that will end up having the same remainder. We can actually do that later and see if it's right. We now have a computer, and it's going to generate random 3-letter words. And as far as we're concerned, any combination of letters is a word. Okay? So, how many words need to be generated to ensure that there is a word in our list that's been generated 8 times? Well, what's the number of possible words? Remember, I said every letter's possible in every place. So it'll be 26 by 26 by 26. There are 17,576 words. They become our holes. So each word that gets spit out, we're going to go, you're in that pigeonhole, you're in that pigeonhole. So they're the holes. So K, that's what we're trying to find. How many words do we have to spit out in order for it to generate it 8 times? So K over 17,576 has to equal 8. So K over 17,576 is in between 7 and 8. It can't be 7, could be 8. Multiply out. We want the smallest number then that's bigger than 123,032. We need to generate 123,033 words to be sure there is a word on that list that has been generated 8 times. No, we won't do that one later. Yeah. Let's have a look at an HSC one from a couple of years ago. A sports association manages 13 teams, decides to check the age of all the players. Any team that has more than 3 players above the age limit is going to get penalised. Now, a total of 41 players are found to be above the age limit. Is any team going to get penalised? Okay, well, 41 into 13 holes, because we think each team is going to be a pigeonhole in this case, and we're placing these illegal players into the appropriate holes. If there is a hole that has, what was the rule? If a team has more than 3 players, they're going to get penalised, so that has to equal 4. By the pigeonhole principle, one team will end up having 4. The ceiling function of 41 on 13 is indeed 4. There will be a team that gets penalised. Alright, so 14H is playing with this idea of the pigeonhole principle,